Hey everybody, welcome back to this class. In this video, we're just going to go over the Module 5 activity and go over some demos on how to use MATLAB signal analyzer and what logic gates are. Let me share my screen. This is the activity for this week. As you can see, we're going to be introducing logic, power, and control. And just here's some background reading on all the different topics. I've also got a little bit here about soldering, and the soldering activity is going to be optional. We have kind of a limited supply and time to do this, but if you want to practice soldering, then this would be the lab to do so. I'll continue bringing in material for us to use as well. So there's a little bit about power lines, and we're just going to be simulating three-phase power as it would appear on an electric power line, like the big lines that you see outside. So here's the assignment, and we can go ahead and walk through this. So this first part's just reading the background. I'm not going to go over that. Just copy this over. So for this part 2 of the exploration, we're going to be spicing up a DTL 2-input NAND gate. And right, so we're going to use LTspice, and we're going to use this IBM 1401 topology. And I think I've linked that. Yeah, I've linked that on the Canvas page here. This is what that looks like, but let's draw it out first. Oops. We have a diode, some input A that goes into diode, and then input B also tied to the cathode of our diode. These two are tied together, and then we have a resistor divider path to V minus and a resistor path to V plus. And so here's one path to V plus, and then resistor current divider here, or voltage divider down to V minus, which we're going to be tying to ground for our activity. And then this goes into our BJT. Right, so this is the emitter with the arrow coming out. The collector is then connected to the emitter through the base. Right, so this is the base. This is the collector. This is the emitter, an arrow. And then this is, I think we're tying this to ground, and then the path up to R2. So here's another ground. We got the path to R2, back up to V plus. And then this is the output of our gate. So this is the 2-input NAND gate. But what we want to do, right, is break this down into something that we kind of understand more. So let's just go over some truth tables. So we have our two inputs, A and we have B, and we have some output. Right, so out is going to be A NAND B, which is the same as saying not A or not B. So then let's say A is 0, B is 1. Sorry, let's go 0, 0, 0, 1, 1, 0, 1, 1. And the truth table for a NAND gate, right, is going to be, these are both false. So not A is true, not B also true. So this can be true. Right? Same logic here. So A is 0, right? So this can be true. And since A is already true, then we can just move on. And then for 1, 0, right? So not A is false, and then not B is true. And since we have this OR, this is true. And for 1, 1, not A is false, not B is false, and can't be true if they're both false. So this is finally going to be false, right? So I guess a more appropriate way of doing this is 1, 1, 1, 0. So not and means it's not A or it's not B. So then taking a step back and looking back at our circuit, we want to be able to pulse A and B so that we can observe all possible outputs, right? So we have a voltage waveform A, voltage waveform B. Well, A stays off for 1, 2 cycles, 1 cycle, 2 cycles, and then it's on for another 2 cycles. It's on 1 cycle, off for another cycle. And we can draw these lines to indicate our cycles here. And we'll do that in a different color. This is what's called a timing diagram. We can look at different outputs, right? So here's 0, 0, 1, 1, effectively. And if we look at B, so B is on and off, but at a faster rate. So it's 0, 1, 0, 1. So 0, 1, 0, 1. And our expected output is 1, 1, 1, 0. 1, 1, 1, 0. And it gives you instructions on how to set up these pulses, but you're going to use a voltage source, right? And you can change somewhere in the advanced settings to this configuration of a voltage source. And then you'll make some observations on these transitions here and where it might have an unexpected output due to the rise and fall times of our circuit. So we've gone over this. For part 3, right, so this, like I said again, this is going to be optional, but I've got these little cubes. And they have 4 holes screwed in them, right? And we have our bandpass filter here. And it's got these 4 notes, right? So it's got our input. It's got this intermediate node. Just call it int. It's got this output node, and it's got ground. And the idea here is we're going to take some metal screws, right? And you're going to put them into each hole and solder on your different components. So let's just say we've got this path right here, right? So we have our input to the intermediate node, right? And then also these other 4. So the capacitor, this node here also has a path to a resistor that goes to ground. And then another resistor that goes to this output node, and then the capacitor that ties it back to ground. Right, so this is our output. This is our input, and this is ground. So you'll get to play around with that. In part 4, I'll pull up a MATLAB script, or I'll walk you through how to go through one I'll do a phase of 0, and we'll walk through how to use this signal analyzer app after we talk about this ultrasonic distance sensor, ultrasonic sensor and the DC motor. So part 5 is the ultrasonic sensor, and we can just talk about the theory behind this first. So it looks like this in your kit. All right, it's got these sound. It almost looks like a boombox, and I think it has 3 terminals. But basically, we have a transmit end and a receive end, and on one of these, right? So let's say there's an object somewhere out here that's sufficiently large. Well, this transmit end sends out an ultrasonic pulse, and this pulse travels until it hits the wall or the object, and it reflects, right? I mean, so it's not perfectly reflecting like this, but some of the sound waves are reflecting and coming back into the receiver. And what the sensor does is it measures the time from the transmit until it receives it to calculate some distance. And actually, I think one of the senior classes is designing this ultrasonic sensor from scratch, just using discrete components to build it up instead of just having this module itself. Kind of neat. It would be an excellent final project for those of you that are looking for something. So, right. So part 6 is the DC motor. We're not going to connect it directly to our Arduino. We're going to connect it to some chip. I think it's L293D, something like that. But there's this chip, right? And it's got some. I think it's got 2 grounds. I've only drawn one here. It's got some positive voltage. It's got some direction. It's got 2 direction pins. I don't remember their exact names. I think it's like M1 and M2 or something along the lines of that. But it's got 2 direction pins, and so one direction, you're going to have direction A, right? So these are digital pins. You're going to set direction A high, direction B low. And then for the other direction, you're going to set direction A low and direction B high. And there's also another pin, like speed, kind of like a speed control pin, where you send a pulse width modulation signal to it with a duty cycle between 0 and 100%. And that controls the speed of our DC motor, right? So some of these pins go to the Arduino, some of these pins will go to the motor. And we're also going to need to use the voltage regulator in our kit to make sure that we don't damage any components or our computer. It talks about that in the user manual. So when you get to the DC motor set, make sure to read over that. So with that, right, we've gone over these 2 more or less. Now we can go ahead and walk through some MATLAB demonstrations here. So here is my screen now, I believe. So I'm opening up MATLAB. Okay, let's start over here. So MATLAB, the first thing that I usually like to do, right, other than starting off with a file name, so file with demos.m, author, and revision date. One thing that you should try to do is clear CLC, close all. So clear, I think, closes all the, or clears up your workspace. CLC, CLC and close all kind of have to do with the figures that you have opened up. But I just like to prefix my script with these three commands. Right, so we're simulating this function. So we have v as a function of t is 120 volts times the cosine of 2 pi ft plus phi. So just looking at this, the first thing that we're going to need, or I guess we can start with what we have. So we know the frequency is 60 hertz. We know then that our period is 1 over f, right? And I will be doing this with a zero radian offset here. So then we have all of that. We also have that the voltage, the RMS voltage here, so V, let's just call it VRMS, is equal to 120. Right, so here's all the things that we are given, more or less. I guess we'll put this phi on a separate line, right, because we'll have multiple phis. I'll just put another example here for you. So phi2 is going to be 2 pi over 3. And then we can start to make our waveform. But before we do that, we need an abscissa, right? So we need our t. We need our t. So our t, it specifies to put over 1 period. So we'll just call this lowercase t, and we're going to set that equal to, we're going to step from 0 to our period t. And what this is going to do, the way that it's written right now, is I believe it's just going to give us zeros, but I can go ahead and run that just to confirm. All right, so over here, you can see that our t is just 0. Right, so this takes the form start, step, stop. So we're going from 0 to t, and t is 1/60th. And so by default, our step size is just going to be 1. It's going to be like discrete integer values, but that's not what we want. We want to sample this. So we need some sampling frequency. So fs, we're going to sample at 4 times the 4 times the frequency, the highest frequency present, which is going to be 60 hertz. So we're going to start at 0. We're going to step every time we have 1/4 of them. We're gonna grab fs samples, right? So we're gonna step 1 divided by fs times all the way up to t. So that's kind of this logic here. So now if we run that, you can look over here in our workspace. We have all of our values, and it looks like t is still. Oh, sorry, this is not the. There we go. So now our t. So we can look at the size of t, and t has 5 samples now. So that should be sufficient, I think. And then if we go to apps and signal analyzer, I think this is assuming that you have the communications toolbox installed, which we did for some previous activity. Oh, so we have our T, but what we want, right, is our V1. So V1, right, so this Vn in general is going to be these different phase shifts, but V1 is going to be 120 times cosine 2 times pi times f times t plus V1. Now I think if we run this, go to editor, hit run, have our V1 here, and it pops up in our workspace here. So to plot them in the signal analyzer, we just drag it up into filter signals, or this little plot here, and there's that. So that's not quite what I'm looking for. Maybe we need to sample more. So let's sample at 10 times frequency. Now it's 1 by 11. I'm going to delete this one. This. Yeah, that looks a little bit better. Cool. Maybe just for look a little bit better, we can sample 100 times here. We go back to our work, and then we can plot V1. There we go. So let's sample at 100 times the frequency here. So we have one. Your goal is to plot the other two, right? And you should be able to just do that directly on here. But all that really involves is pretty much copying this, changing this to V2, changing this to V2, running it, making sure that it pops up in our workspace here, going back to this app, dragging it up here, plotting it. And there's one more signal where you just plot the sum of all three of them. And this is kind of like what the LTspice part looks like once you get it in started. So with that, I think that's all I wanted to talk about here. So thanks for tuning in. I'll see you guys next time.